All right, this video here is our first video for Chapter 3, where we're going to take a look at derivatives. It's a pretty big day, actually. We're going to start off by just kind of reviewing the idea of differentiability and where derivatives come from, and then we're going to look at how you can do derivatives really fast. So we're over here on page 2, and we begin just with this numerical problem, just nothing but numbers in a table. We don't actually know the algebra behind that function f of x. And the first thing says, hey, can you calculate the average rate of change of f of x on an interval from 0 out to 2? Key thing to notice here is this average, right? So we're going to be doing a slope, but we're going to be doing an average slope. And I'll see if I can actually just use some colors here to keep track of all the different things that are happening on this page. So this first question has an interval from 0 all the way to 2. So just looking at the x values, that's going from there all the way down to there. So a really large span of x values. Not a derivative here at all, just an average slope, kind of a grade 10 deal. And if you're asked to do this, it's nothing more than grade 10, where we're going to look at the difference in y values and divide by the difference of the x values. So the final y value is up there at 2, and the original y value is negative 2. So we have 2 minus negative 2, all sitting on top of the run. And it looks like we go from 0 to 2. So final minus initial. Okay, it looks like we've got 4 over 2. It terminates nicely. We'll just call the answer 2. So that's an average slope, kind of a grade 10 deal. And then now everything below question A, all this stuff down here is going to be derivatives, or at least attempts at derivatives, where we're going to do some estimates. And I want to show you a few different situations. First one here says, can you come up with an estimate, your best guess of the derivative at 1.74 for x? Now 1.74 is not in the table. Okay, it's a number that's in between two x values that are there. And just looking on the table, let's go purple with this. 1.74, that's between the 1.6 and the 1.8. That's like right in there. And so if I had to do my best guess of the derivative at a number in between those two x values, what I would do is say, well, let's do a very small average rate of change. Let's take the points that are right before and right after that. So the final y value after that is 1.888. And then the one right before it is 1.584. And then the difference in the x values, well, we finish up at a 1.8 and then subtract the 1.6. So I'm not really too worried about the answer. You know, if you want to know what it is, it's 1.52. Okay, great. That's all very nice. But what's the key thing? If you're asked to try to do an estimate of the derivative, for an x value that's in between two rows, take the row that's immediately before and after it, and then go from there. That's the only acceptable way to do your best estimate of the derivative. This next one is interesting. It actually has 3 acceptable answers. We're going to try to find the best guess of the derivative at -1 for x. Okay, well, let's just go and take a look at where -1 is. It is actually in the table. Okay, so there's a table value for -1 right here, and they're saying, what's your best guess of the derivative? So it's not straddled in between two numbers. It's actually right on that row there. Okay, so here are some options. You could do your left approximation, where you would actually look at the point immediately left of the point you want, and then up to that point. So you could go from there to there, from -1.2 to -1. And you could do a slope based on that. So this is your kind of left estimate of the slope. And as I go and just do my grade 10 slope calculations, pretty boring here now. It's just going to be a change in y over a change in x. That's the best I can do. Well, for that spot in the table, the final y value was 2, and the original y value was 4.048. And then x values, final x value would be the -1, and then beginning just before that at -1.2. And when you run those numbers, it ends up being negative. Hey, sometimes slopes are negative, -10.24. So that's one option. You could do the left estimate. Another option would be to say, well, why go before that point and then up to that point? Why not go from that point to a spot after it, right? So I could say, okay, let's go from -1 to -0.8. That's totally fine as well. Let's call that the kind of right estimate. Just going to do a grade 10 slope And thinking about what that graph would look like, I'm taking the point that's on the -1 and then going 1 just to the right of it. Final y value would be 0.432, that's right off the table, minus 2, and then the difference in the x values. We would finish at minus 0.8 and we would begin at -1. And the value for that is not the same, and that's okay. You could have either one of those answers. You don't have to have them both. You could have either one, and it's totally fine. There's even another option here. We could say, well, why should we favor left or why should we favor right? You could actually do a symmetric calculation, which is what a lot of graphing calculators do. Why don't we try the spot just before and just after? Let's go from -1.2 up to -0.8. Okay, so I'm going to call this the symmetric approximation. Not really playing favorites here at all, right? Looking at the slope for that. Again, it's just going to be a grade 10 slope calculation. Final y value is 0.432. That's just directly off the table. The original y value would be 4.048. And then the difference in the x's, final x would be -0.8, and the original one would be -1.2. Now the number ends up being -9.04. To be honest, I don't really care too much about the number. Just want to point out that when you're asked to find the estimate of an x value that is actually occurring in the table, and if the spacing before and after it is the same, those are all 0.2 away, you could either do left or right, or you could do symmetric. And that's a little bit different than this last one, trying to estimate the slope at 2.2. That's also in the table, but I'm going to suggest to you that there are only two good ways that you should do this, two ways that are acceptable. Taking a look at this x value right here at 2.2. Here's what's different between the last one. When we were doing the -1, the option to go from the left side is only 0.2 back, and the one to the right is 0.2 forward. But here, when I look at the choices here, from 2 to 2.2 is a small jump of 0.2, but from 2.2 to 2.6 is much bigger. And so it would actually be reasonable to say, well, no, you shouldn't go and do the 2.2 to 2.6 jump when you could have done a smaller one. So I would suggest to you that in this case, what we could do is we could go and do a left approximation. That would be totally fine, right? So from 2 up to 2.2 is okay. Let's go and do that. So that slope, just going to do a grade 10 slope calculation, nothing really creative here. We would finish at a y value of 1.872 and an original y value of 2, all over 2.2 minus 2. So that's only a delta x of 0.2. That's pretty reasonable. That's better than the other delta x option of doing the right approximation. This ends up being -0.64. Now, that's probably the one that I would do, right, because it's fairly close. There is still some honor, if you wish, in doing the symmetric calculation. For an AP exam, it would be considered acceptable for you to do that. Let's pick a color I haven't used here yet. I don't know, how about this bright green? So you could say, well, I'm going to go from 2 all the way to 2.6. That's saying, hey, I'm not going to play favorites, and I know the gap from 2.2 to 2.6 is a bit bigger, but that would be okay. And so you could say, hey, this is my estimate of the derivative. And these are all just estimates of the exact slope of a tangent line, but it's the best we can do with the table. And speaking of the table, it's the table where I go and grab these y values. So I would just go and rip those off. I know this is a pretty large run along the bottom of 0.6. That's why personally, I probably would go with the option over here on the left of -0.64, but this is considered an acceptable answer. Okay, either one of those two. So it's a little different than question, oh, is this mislabeled up here? Yeah, this should have been a C. That's an oops. It's a little bit better than option C, where you had 3 choices. You've only got the 2. You can go with that close approximation, which was on the left, or you could do the symmetric one. So those are your options when you're working just straight off of a table. Okay, on the next page, let's just kind of go over this word differentiability and how it talks about how there's a very clear tangent line in the story. And I've got this graph. It looks like it's built together in pieces. It's some sort of function by piece. And I want to explore two different spots on this graph. One of the places I want to look at is going to be this point right here at x is equal to 1. Okay, we'll talk about that in this box up above. And then the other one will be this point here at x is equal to -2. Maybe we'll discuss that down in the box down here. But let's go with the top one first. Okay, so up here at x is equal to 1, what kind of things can we say are true? First of all, let's check to see if this graph is continuous. Now I know just, layman's terms, can you draw that graph without lifting your pencil? Yeah, it's true. But what you'd have to say if somebody said, well, justify that you think this is continuous, you would have to say, when I watch the y values and consider them as a limit, as x approaches this, x is equal to 1 from the low side, okay, coming in from the left, if I consider that function's y value, and then I ask myself, well, what is the function at 1? Is there a dot there? Yeah, there is. And then what about on the other side as I come in as a limit, approaching 1 from the high side? Are all three of those the same? And the answer is yes, they absolutely are. So as soon as you can see that all three of those y values are the same, you can say, well, that's continuous. And so if people just ask you, is it continuous? You can say, yeah, sure. But if they say justify it, you have to write down all three of those things and say, look, the left limit is equal to the function is equal to the right limit. And if you don't write that down, you haven't actually fully justified it, and you wouldn't receive full marks on an AP exam for that. Okay, now let's talk about the derivative. Let's talk about the slope just before and just after that point. It doesn't look to me like they're the same. In fact, they're not. The slope of this purple line is 2. And the slope of this green line as it wanders away is -1/2. And so if somebody was to ask you, hey, what do you think about this? What about doing a limit and thinking about a calculation of the slope, with that Newton's limit? Could we say, hey, what's f at 1 plus h minus f at 1 all divided by h? But I want to actually wander back. So I could say, well, let's have h go to 0, but from the low side. Let's use slightly negative numbers. And then let me go and check and see, hey, what's that Newton's limit doing? What's the derivative calculation looking like if I go 1 plus h minus f of 1 all over h? But let's go with h's that are just slightly positive. Very small, but slightly positive. And what you find is these two are not actually the same. In fact, the one on the left is a slope of 2, and the one on the right is a slope of -1/2. So I would say, oh, hey, that didn't work out to be the same value. This thing is not differentiable. Not at that point anyways. It's definitely got a little cusp in the graph. Maybe another way you could say that is, what if we were to look at the derivative? What if we looked at the slope value? And what if we thought about it as a limit and said, hey, what are you doing when x approaches 1 but from the low side? Are you the same thing as what that derivative is doing, that slope of the tangent line, when x goes and approaches 1 from the high side? So both the blue and the green kind of say the same thing. And this is also a does not equal. One of them is 2, and the other one is -1/2. And so that thing is not differentiable. Okay, but the nice thing is this graph does actually have differentiability at x is equal to -2. So let's just kind of look at that and how we could write that mathematically. I mean, we could look at it and say, yeah, it's connected and it's smooth, right? Nice, easy adjectives. But what does it say to actually do that? Like, how do you go and say that mathematically? And that would be like this. You'd have to say, hey, when I watch the limit of the y value, just looking at the function, not doing a derivative here yet, x is approaching -2, but from the low side. Are you the same thing as the function at -2? And are you the same thing as the limit of that y value when x approaches -2, but from the high side? And the answer is yeah. All of those are actually equal to this one y value here of -2. So that checks out. And that's what you would have to write in order to verify that this graph is continuous at x is equal to -2. You have to write those three things down. Okay, what about the slope though? Is this thing also differentiable? And the answer is yes. if you were to go and do a slope calculation as a limit, and we won't do very many more of these as limits, but if you did, if you were to say, hey, what's the limit, try this again here, of this grade 10 slope calculation turned into a limit to make it like calculus, f at -2 plus h minus f at -2 all divided by 8. That's a derivative calculation, but let's make sure we're working with small values that are a little less than 0. So we're actually a little bit before -2. You know, are u equal to this grade 10 slope calculation taken to a limit? We'll do this slope calculation at -2. But this time let's go with h's that are just a little bit bigger than 0. And so you're checking out the slope just before and just after this point, x is equal to -2. And what you find is in both cases, they share the exact same slope. You have 2 is equal to 2. So you can say, hey, this thing checks out. This thing is differentiable. Okay, so what's the point of this page, right? Let's kind of look at this big picture. Just to use some really casual words, if somebody says, oh, hey, that thing is continuous, well, then they're saying it's connected. And if they say it's differentiable, then in nice simple words, they're saying, oh, it's smooth. But what you have to do is argue that mathematically by writing down all those limit statements, right? So it's one thing to say, yeah, I can look at it. I can see that it's connected. I can see that it's smooth. But it's another thing to take it to that level mathematically where you can write down the proof for that. Okay, well, let's continue on with this idea of looking at these derivatives, these things that are the slope of the graph. I'm going to start doing some sketching here. Okay, so we're over the page into part C. And we're going to check out this function g of x shown below, and then part A says, can you sketch the derivative right on the same graph? Now, to accomplish that task of sketching the derivative right on the same piece of graph paper, geez, it might be helpful to look ahead to part B. For what x values? So at what locations is the rate of change? Okay, well, when you see that phrase rate of change, that just means slope, right? So for what x values is the slope of the function 0? Where is that graph that I've got here in red flat? Well, I can see it's occurring at a couple of spots. It's occurring here and there, okay, at a couple of different x values. So I can say, yeah, I'm seeing this happen at x is equal to 0 and also at x is equal to 2. So if I was graphing the derivative, a record of what the slope is at any moment, then I know at least at those two moments, you know, at this moment here and at that moment there, the graph that I'm about to sketch has to be hitting 0. It has to record the fact that that red graph has a slope of 0. So I'm going to begin my sketch now of the derivative, and I have to be hitting 0 here and hitting 0 there. Okay. Part C, again, still kind of avoiding part A. For what x values is the rate of change, that just means slope, of the function positive? Well, where is that red graph going in a positive slope? That means as you move from left to right, you have to see the graph going up. And so I'm looking at this graph saying, okay, if I view it from left to right, it looks like all in this section in, no, that was a bit of an ugly looking bracket. Let's try that again. All in there, it looks like the slope of this graph is positive. So g prime of x, the derivative, has to be a positive thing here. Okay, so to describe that, where's the rate of change positive? I would probably say, well, stuck in between 0 and 2. Those are places where that's happening. And so when I go to sketch this, I'm going to have to draw this graph. I'm going to draw it in blue. And I have to show that it's positive. Don't worry about whether it's going up or going down. You just have to make sure that you draw it up here and not down here. I want to show positive values for this blue graph. Now, another thing to note is the slope of the red graph is probably at its peak in terms of positive values at x is equal to 1. I don't really know how steep it is there. Maybe, I don't know, a little bit more than a slope of 1. Slope of 2 or so, maybe a little more. So it's probably going to peak up around here, and all in this area, I'm going to be graphing positive values for that blue graph. Now, I know when I draw this blue graph, like right here, I'm drawing it going down, but it's still a positive graph up until that spot at x is equal to 2. And so that's saying that the slope of the red line here is positive, maybe diminishing, but even here, like right there, the slope of that red graph is still positive, but only barely. And sure enough, the graph of the blue graph is positive, but only barely. Don't worry about the fact that the blue graph is pointing down at that point. It's not what we're looking at today. Now, finishing this off, what's going on with the slope of the red graph in here? Well, it's all negative slope, so I have to be down in my negatives down here for my blue graph. In fact, it's a very aggressive negative slope, then less negative, and then just slightly negative. And so that's going to look like this. So everything that I just drew was actually in the negatives, and it was just becoming less and less negative. Then, for the last part, all along here, this red graph has a slope that's negative. In fact, it gets more aggressively negative as I move to the right. So I want to be drawing stuff not up here where things are positive. I want to show that this derivative graph has to be down in the negatives. It's going to have to be like that. And so that's our sketch. Just showing, it's making a record of the slope of the red graph. Okay? The y values on the blue graph are the slopes on the red graph. Let's try this again with this next example. Example 3, see if you can match the graph of the functions with the derivative down below. So we've got a couple of different questions that we're going to go and look at, and then there are possible answers down below. It's kind of like multiple choice. So things that I would look at, okay, looking at this graph here of the function, right there, the function's looking pretty flat. So that's telling me that the slope of this graph is flat, and the slope of the graph is what we call f prime, and so I'm expecting it to be 0 there. So I'm looking for a graph for my optional answers here that has a 0 recorded value at x is equal to 0. Well, they all do, so that's not super helpful. Let's look at some other spots. Like how about here? All along this section, it looks like the slope of this graph, I mean, you could call it m, right, like in grade 10. That derivative, it's positive here. And in here, it's also positive. I know you might sketch it backwards, but as you move from left to right, this is heading uphill. It's got a positive slope to it. So I would say that the derivative, right, this record of the slope, this f prime, it has to be positive here as well. So I start looking for answers here. I'm looking for an answer that as I stare at it, in this whole section out here, I have to be seeing a positive graph, and out here I have to see a positive graph, and then just 0 right in the middle. And the only option that seems to do that is option A. So A is going to be the derivative for that one. Okay, number 2, plan of attack. Let's look for flat spots first. Looks like this graph is flat here, and here, and here. So I'm looking for a possible answer that has zeros recorded at those 3 places. The graph's going to hit the x-axis in those 3 spots. Other things to note, it looks like this graph is in this section right here. It's heading uphill. F prime is positive. And in this section here, looks like f prime is positive. But then there are these other places, like right in here, where the graph is going downhill, so f prime is negative. And in here, f prime is negative. So I'm looking for a graph that at the beginning is just negative, then 0, then positive for a while, then 0, then negative for a while, then 0, then positive. And when I say it's 0, it's positive, I mean its y values will look like that. And so for me, that's actually C. Okay, here are the places that record where the graph up above is flat, and I can see that before the first blue dot, I'm in the negatives, then in the positives, then in the negatives, then in the positives. Yeah, this one's definitely going to be option C. So the task here is to look at the slope of the graph of f and say, okay, the slope of f, which is in the top in this story, has to be the y value of f prime. Those are the graphs down below. All right, let's keep trying this game of linking the 2 graphs together. Okay, example 4. Complete the sketches of f and f prime given some information. Okay, well, for this number 4, they're telling me all about f. It's built in pieces, but they're completely telling me about it. So I'm going to start sketching this thing. It says, for a while, just graph f is equal to -1. In other words, y is equal to -1. Just graph that, nice flat line, until you get to -1 for x. So I would just be drawing it like that. And I'm not even allowed to draw this at -1. It has a strict inequality there, so I'd put a little open circle. Actually, let's make that a little bigger. It could be easier later. There we go. Now, the next part of the graph, it's actually a parabola that's been pulled down by 2. And you can use your graphing calculator to help you out with that. So if you graph y equals x squared minus 2, yeah, it's just been pulled down a little bit. And you're allowed to graph that during this window of time from -1 for x up to 2. Now, this one actually connects. This parabola at -1 is like right there. So that's perfect. It's a nice connected graph. It's continuous, right? And then this graph goes like this. And I'm allowed to graph it at 2, so I'm going to stop. Final thing to graph is y is equal to 3 minus x. Or if you want to think of it in a different way, y is equal to -x plus 3. So a y-intercept of 3 and a slope of -1. And you can't begin to draw this until after 2. And so you can't draw it until like after here. And so that graph looks like that. It doesn't actually touch there, right? There's no connection there at that spot. Okay, now they're saying, well, can you try to graph the derivative? Well, parts of this are very easy. The first section there, where I was graphing y was equal to -1, the slope of that first section is actually just 0. So when I go to draw the derivative, I'm going to say, yeah, the graph up above has a slope of 0 all along here until I get to this spot. I'm just going to leave a little open circle for now. We'll decide if we can fill it in later. Hey, the other one that's pretty easy is the final part. It's a line that has a slope of -1. So I can say, oh yeah, by the way, after you get to x is equal to 2, the slope of the upper graph there is just steady at -1. But what about that parabola there in the middle? You can use your graphing calculator if you want to, right? If you're like, I don't know, what is the slope? Pretty soon we'll look at a quick way to do this. But if you would rather use this as a little bit of a help and say, hey, let me just see this thing, right? So there's the graph. What is the slope right there at -1? Just say, hey, calculator, help me out. Please calculate a slope, which is number 6, and then just type in -1. And it'll say, oh, the slope there is -2. Oh, okay, that's helpful. Well, the slope here I can see is 0. What about the slope at 1? So calculate a slope at 1. And it says, oh, the slope there is 2. Okay, I'm going to do one more. What about the slope of this parabola at x is equal to 2? So calculate a slope at 2. It says, oh, by now you're up to 4. Okay, so I can use that as a guide for now. Looks like we're going to go from a slope of -2 down here, open circles for now, all the way up to a slope of 4 at the end. And it's actually just a steady, smooth transition from one slope to the other. Okay, now let's see if we can fill in any of these little circles. I know I'm looking at the picture up above, right? And yeah, there's some filled in spots here, right? Where it says it can equal it. Okay, so sure, the graph that I have in blue has some filled in dots. But then you ask yourself, is there a very clear tangent line like right here at x is equal to -1 or right here at x is equal to 2? And the answer is no, there isn't. There's just no clear idea for how we should draw a tangent line in here. I don't know, so many options. So we just don't. We don't draw a tangent line in there. And we're not going to draw a tangent line in here. Like, how would this, that's not going to work at all. So there's no clear tangent line. And so we have to tell people that there's no clear value for f prime. And we're going to do that by leaving those circles open. If we were to go and fill them in and say, oh yeah, well look, we're going to go and fill this in like that, then you're saying, oh yeah, the slope at 2 is 4, and I don't know that there's a tangent. I know there isn't a tangent line there with a slope of 4, so I don't want to fill those in. All right, where is the original graph f of x not continuous? Where is it discontinuous? where is it broken? Where does the left limit, the right limit, the function not all equal? And the answer is in this story at x is equal to 2. Where is it not differentiable? Right? Well, I can see that on this graph. No value for the derivative there and there. Or I can see it on the graph up above where there are no tangent lines. So I would say, oh, at x is equal to -1 and 2. Those are places where this upper graph in blue does not have a clear tangent line that I can draw in. It just doesn't exist. So those are places that are not differentiable. Points of non-differentiability. The next thing, where is it continuous but not differentiable? Well, just from looking at the two answers I just wrote down, it looks like it was continuous at -1, but it wasn't differentiable there. And now the other way around, where is the graph smooth but not connected? Well, it's a bit of a trick question. This never happens. It can't happen. Not ever going to happen on a graph. You must be at least connected before you can be smooth. Okay, the example right beside it. Let's take a look at this one here. Example 5. Some additional information. We know that the function at 0 is supposed to be -1. Okay, thanks for helping me out. So I can go and put that point in. And this function is continuous. In other words, this function is connected. I'm supposed to be able to draw a graph with my pencil without ever lifting it, apparently. Well, that's all they're telling me up there. There must be some information down here. Oh, here's the derivative. Well, the derivative comes in pieces. So they're saying the derivative, the slope of the upper graph, is -1 for a very long time. Okay, well, I'm just going to go graph that. In fact, it's -1 until you get to x equals 1, or at least until just before it. Then a big open circle, because it's got that strict inequality there. Then the derivative, the slope of the upper graph, just goes click and switches to a 2. And jumps to that. Okay, well, that graph has no value for f prime at x is equal to 1. There's no equal sign option in there. So this graph in green is not a continuous graph. But what's interesting is they're saying up here that I'm supposed to be able to draw a graph that is continuous. Well, the graph down below, the graph in green, is telling you what the slope looks like for the graph up here in blue. So for the longest time, the slope is supposed to be -1. So I can take my ruler and just pitch it with a slope of -1, kind of down at a 45-degree angle, and say, hey, you know what? I got to draw a graph that looks like this for a long time until I get to this transition, which is going to happen right there. Then this graph is going to switch to having a slope at 2. Now, if they did not put in this little bit of information right here, if they didn't say, oh, by the way, it's connected, then I might mistakenly go, I don't know, hey, whatever, as long as it's got a slope of 2. How about we go and draw a graph that looks like this? Because that line's got a slope of 2, right? Oh, maybe I wouldn't graph it right there at the beginning, maybe from about here, right? I might say, yeah, there. But they said that this thing is going to be connected. So I'm going to go and bring that down until it touches like that, right? Or maybe if I just draw it all again here. If you're going to tell me that this thing is a continuous function, then I guess it does actually have to touch there like that. So the graph in blue is connected at x is equal to 1, but it's not differentiable there. There's no clear tangent line that I could draw in, right? And that's what this is saying, right? It's like, yep, sorry, no answer for you when x is equal to 1. Hey, there was one little follow-up question here. What did they ask? Oh, there it is. Where is it not differentiable? Yeah, it's not differentiable at x is equal to 1. It's connected, it's continuous, but it's not actually differentiable there. Okay, so just again, we're looking at those connections between the graph and its derivative, which is a record of its slope. Well, that's kind of been some review, actually, of the last chapter. Now we finally get to get this thing started. And just like starting a car, we're going to just go and turn the key on these things. We're not going to worry about like taking the engine apart. We're not going to worry about doing the limits. We're just going to get in the car and drive away. And that can be done with derivatives just by exercising a few neat little rules. And so you're going to find that we don't do derivatives with limits from this page on. Instead, we just quickly look at it and say, hey, this is going to be the answer. First rule, what is the derivative of a function that's just a constant, like this one, y equals 14? Well, you know, if you graphed that, y equals 14 is just a flat line, like way up there at 14, and its slope is always 0. So the slope of this one all day long is equal to nothing. The same thing with this graph, y equals -8. That's just a line that's like down there. It's still flat. So we're going to say, yep, that one's also got a derivative that is always 0. So here's the rule. If you ever do a derivative of a constant, here's Newton's notation with the apostrophe, or Leibniz's with this ddx. We're just going to say, oh yeah, super easy. The answer is 0. All right, what's the derivative of 0? Well, that's a very boring graph, and its derivative is just as boring, 0. Even a nice irrational number like pi, the derivative of that, 0. This thing, sine of pi over 6, like sine of 30 degrees, right? Well, that's 0.5. Yeah, y equals 0.5. Flat line, derivative 0. This one here, this one is interesting. It says, oh, let's do a derivative. And then right here, this says the derivative of whatever that is, f of 2. Well, that's actually just some sort of constant where you go to the graph and you find out what is the y value at 2. It might be 14, like the very first example here. So the derivative of this is actually going to be 0 again. So I know this notation here is a little bit odd, and I've got it there deliberately because I just wanted to point out that this is not the same thing as saying, oh, can you go and find the derivative at 2? This says find the y value at 2, then take its derivative, right? Well, that's going to be a constant, so the derivative is going to be 0. Next rule, probably our most popular rule, super nice. What if you're doing the derivative of a power, like this x to the 4th? I do not want to do this with limits, where I would have x plus h all to the 4th power. You would be there forever trying to do that. Well, here's the rule. It's kind of like the exponent falls down out front and becomes a coefficient. So it's n times x to the n minus 1. So it's like hiding behind that exponent is another little number that's 1 less, and the number on the surface falls down out front and becomes a coefficient. It's easier just to show you this as opposed to trying to describe it. So the derivative of x to the 4th would actually just be 4. The 4 falls down. X to the 3, lower the 4 by 1. This one is kind of like saying x to the 1. And so the derivative would be the 1 comes down and then x to the 0. But x to the 0 is just 1. So this is just 1. This game even works for irrational numbers. There's no change to the plan. So the derivative here is pi times x to the pi minus 1. No problems with irrational exponents. Even negative exponents, no troubles for this rule. So this would be -8 x to the, now be careful, you've got to go down by 1. That would actually be -9. Don't be shocked if you check the back of the book and they say, oh, we're going to write it like this, a -8 on top of an x to the 9th. Of course, that's the same thing. This next question, well, we don't actually know how to do fractions of algebra yet, so what I would do is change the question. We'll do this a lot. We'll turn questions into nicer questions. So believe it or not, that's a nicer question because now that's the power rule. And then we can say, oh, okay, well, here's the derivative. It's going to be -5, x to the, lower it by 1, -6. So this could be -5 all on top of x to the 6th. This game works with decimal exponents as well. You really can't hurt it. So we can go 1.4 x to the, lower it by 1, 0.4. You can even play around with nice roots like this. You can say, hey, let me rewrite this question. I can think of that as being x to the 1/2. There's a new way of looking at that question. And so the derivative, the machine that would exactly tell you the slope of this graph, would be 1/2. X to the, lowering that by 1 would be -1/2. Don't be shocked if you check the back of a textbook and they say, hey, let's write it like this. That 1/2 can be written with a 2 down below. X to the half is a root, and the negative means it's down there too, and they might write it like that. This one, let's rewrite it. This is the same thing as x to the negative 3 all over 2. It's like an x to the 1 multiplied by an x to the half. That's 3/2, but upside down. So just a new way to write the old question. And now the derivative. Lower the exponent down, and then lower the exponent by 1. Don't be shocked if you check the back of a textbook, and instead of writing it like that, they might write it as 1 fraction. I don't think this looks any better, but they might write it like this. -3, all on top of 2, and then you'd have x to the 5/2. Which you could even write as like x to the 5th under a root sign, right? If you think that looks any better. I'm going to do my same game here of rewriting this. This is like x to the 4th multiplied by x to the 2/3. Well, the rule for multiplying powers together is you add the exponents up. So 4 is like 12/3 plus 2/3. That's x to the 14/3. All right, that's getting it ready. Now it's time to actually go and do the derivative. Easy. Drop the exponent down and then lower the exponent by 1. Lower it by 3/3. That would be 11/3. So that's our power rule. It's pretty well indestructible as long as it's some sort of constant that's up there. It could be an irrational constant, fractional constant, doesn't matter, negative constant. It's super, super nice. Okay, we're just going to do a couple more pages here, and then we'll call this lesson done. The next one, the constant multiple rule. I like to describe this rule this way. I could hear me say this in the class all the time. You know, when you have these constants that are kind of in the way, constants just hang around. They don't go anywhere. They don't really cause you any problems. They just hang around. So what does that look like in terms of it operating? Then we'll fill in the box. There's this 4 in front of some nice algebra. I know how to deal with x to the 5th. I just did it on the previous page. So the derivative for this thing, well, that 4 is just going to float around, and then you do the derivative of the x to the 5th. Well, that would be 5x to the 4th. And yeah, you can write that as 20x to the 4th. So that 4 out front was just kind of hanging around. Then the 5 comes down, bumps into it, and turns it into a 20. So the rule officially says this. If you've got a constant multiplied by some algebra, that's what this u of x means, right? Some stuff that's made up out of x's. If you're trying to take the derivative of that, that constant will float around, and then just do what you would normally do. Do your derivative of that algebra stuff, and the constant will still show up in the answer. Let me show you this third one here. Derivative for this, the 8 would hang around, and then I would have to do the derivative of the algebra. I don't even know what the algebra is. They're not telling me. They're just saying it's f of x. So yeah, find out what its derivative is, multiply it by 8. This one here, the n's going to come down. It's going to bump into the a. That a just hangs around. So it's actually like an times x to the n minus 1. Okay, let's exercise the same plan on this. This is like a 7x to the 1. The 7 hangs around. The 1's going to come down. We're going to have 7 times 1, x to the 0. But x to the 0 is just a 1. So the derivative here is just a 7. Which actually makes sense. You know, if you think about the line y equals 7x, it's just a straight line with a slope of 7. Doesn't even have a y-intercept. It's just 0. So yeah, its slope would be 7. Next question, I'd change it. I would say, hey, you're kind of like a 1/5 x to the 5th. So if I was to do a derivative, that 1/5 hangs around, the 5 shows up to the party, bumps into the 1/5, just turns it into a 1. And so the derivative here would just be a 1 x to the 4th when the 1/5 and the 5 touch each other. Next one here, getting into a bit of a rhythm. 4 comes down, bumps into the negative 12 that's just hanging around. So you're going to have a negative 48 x cubed. I'm going to rewrite this one. This is like 3x to the negative 6. Okay, so y prime would be, the 3 hangs around and the negative 6 shows up, so we're going to have a negative 18, x to the negative 7. Okay, so that's the constant multiple rule. Constant's just going to float around. One more main rule for today. This one's actually quite nice. It's what you'd kind of hope would happen. You know, what if you have some stuff that's all added or subtracted together? Like look at the first example there. X to the 8th, 5x to the 7th, a minus x, and a 9. I know how to do the derivative of all of those things individually, right? Like just the 8x to the 8 or the 5x to the 7th. Well, what about when they're added or subtracted in a polynomial? And the good news is it's quite nice. Just do them separately. Easy stuff. So if I had to do a derivative of this polynomial, I would say, well, let's just do a derivative of u, and we'll do a derivative of v, whatever that is. Just do your job. And then, hey, if it's a plus in there, we'll put a plus. If there had been a minus in there, I'd put a minus. It's probably easier to show you this than it is to describe it. It's this easy. Derivative would be 8. X to the 7th. There, I did the first one. Here comes the next one. It's going to be a 35, x to the 6th, and it's a plus, so plus 35, x to the 6th. Derivative of x is just a 1, so minus a 1. Derivative of 9 is 0. Okay, won't even write anything down. If I was doing a derivative of this one, that's kind of a weird looking apostrophe. There we go. The 2 comes down, it would be 2a times x to the 1 plus the 1 comes down plus b and then plus 0. Okay, what about this? What's going on here? Oh, don't get tripped up here. That, I don't know what it is. I'm not sure of its value, but I can tell you that that's just a constant of some kind. And I know that the derivative of a constant is the most boring thing ever. The slope of a constant graph is just 0. So this could go pretty quick. If I had to do a derivative here, I would say the derivative of that, 7 hangs around, f prime, so I just did a constant multiple rule. Oh, then a difference, minus, the 3 hangs around, do a derivative of the g, and then, yeah, like minus 0. You don't even have to put that on there. This one here, we don't yet know how to deal with algebra that's multiplied by algebra. So my advice, and this is true for so much of calculus, simplify if you can. And right now you need to do that because you haven't seen all the rules yet. I could rewrite this story and say, hey, here's the function that we're trying to take a derivative of. So there's no apostrophe there. Right, just preparing this thing. This is 12 x to the 8th minus 32 just an x. Now I'm going to go and do the derivative. So tidy stuff up if you can do that. Derivative here, 12 times 8, that's 96 x to the 7th minus a 32. Done. Okay, final page. Sometimes you want to actually go and do a derivative of a derivative, sometimes even beyond that. And so we're going to have to look at how do you write that down. Process of doing it is actually really easy. In fact, let's do that first. Let's do all the derivatives here. So I've got this function, f of x or y, whatever you want to call it, is x to the 4th. And then we're just going to start hitting this thing with derivatives. So the first derivative, the 4 comes down and you'd have 4x to the 3. Yeah, that's written right here. Well, let's keep going. If I did one more derivative, I'd have the 3 come down, bump into the 4, and I would have 12x squared. And if I did another derivative, the 2 would come down and I would have 24x to the 1. Well, most people just write that as 24x. And if I did a derivative again, it's kind of like asking, hey, what's the slope of the line y equals 24x? Well, it's just got a slope of 24. And then if I do the slope of a constant function, I get 0. So often these derivatives will start to get simpler and simpler and sometimes just turn into 0. But the whole idea of the top half of this page is, how do we name that? How do we write that down? Now, Newton's got a neat little technique for doing that. He's like, well, let's just use apostrophes. So we've got y prime, or if you wish, sometimes he explicitly puts the x on the end to just say, hey, it's made up of x's, you know. Like, look, there's an x in here, right? X cubed. The next derivative is y with 2 apostrophes, and we pronounce that as y double prime. You want to do another derivative? Y triple prime. And sometimes people like to just explicitly show that it's a function of x. Now, after 3, it gets hard to count the apostrophes. You start to get like double vision. So we put in round brackets the derivative number. Without the round brackets, it would look like an exponent. We wouldn't want that. So we're just going to go like that. And some people like to say of x, right? It's kind of optional. And again, 5th derivative. Anything higher than 3 derivatives, we'll just write down the derivative number. You can do that with the letter f as well instead of using y. So you could say, oh yeah, how about f double prime of x for the 2nd derivative, or f triple prime of x. And then again, we're going to switch and just use some round brackets to count the derivative number. Okay, so that's Isaac Newton. He liked the apostrophes. Leibniz liked to actually show what he was using to take what variable he was using for the derivative. That's why he's got the little dx down in the bottom. Now, I want to show you this a few different ways. For the first derivative, people will write it like this, or they might prefer to write it as ddx, which is kind of an instruction. It says, let's go do a derivative. And then they put the y like that. Same thing with this notation here. You could also write it as ddx, which is an instruction. Go do a derivative. And you're like, derivative of what? Of f of x. And then once you get to the 2nd and higher derivatives, people don't typically write it like that. Instead, they would write it this way. They would say, I'm going to do 2 derivatives of y, and both times I'm going to use x's as my variable. There's only the single 2 down there in the bottom. There's no 2 on the d. You could also write that with the f of x notation like this. 2 derivatives of f of x are done, and both times I'm going to use x. Yeah, it's a little more time consuming than writing the apostrophes, but it's very clear about what you're doing. 3rd derivative, either written with y or with f of x. 4th derivative, if you want to keep doing this. You can do that with f of x as well. And we can keep playing the game. Let's stop here at the 5th. Okay. So those are just derivatives of derivatives. Let's try a couple of examples out here. This first one. Wow, pretty complicated notation. Let's see if we can figure this out. What's happening here? This is asking you to find the 2nd derivative. Okay, so we can do that. Now this next part, this evaluation bar right there, that says when you're done, once you've found that 2nd derivative, go and do an evaluation. But you have to do the derivative first. Okay, well, we need to do a couple of derivatives. We have the function there. Let's go for the first derivative. So df of x dx. All right, using my derivative rules, that'll be 24x squared plus 8x plus 1. I'm getting quicker at this. Then the next derivative. Got to find the 2nd derivative. So I'm going to do a derivative of that derivative. The slope of the slope. Okay, that would be 48x plus 8. So it depends on the x value. I need to know what the x value is in order for me to evaluate this. And they're saying, yep, yeah, we want you to go and evaluate it now at -2. So if it was Isaac Newton, he would write it like this. He would say, why don't you do the second derivative and then figure it out at -2. That's a nice, quick, compressed notation. With Leibniz's notation, he says, no, I have to write it like this. You do the second derivative first, get that done, and then go and evaluate this at x is equal to -2. Okay, well, I'm going to go and put the -2 in now. So I'm going to have 48 multiplied by -2 plus 8. So I think the answer ends up being -88. Now, example 11, the one we're going to finish with. This one here, it's actually, I'm going to make a guess that somebody's kind of mixed up their notation here a little bit. If they didn't, then I would definitely say that this is a trick question. It might not be asking what you think it is. This is actually not saying to go find the second derivative and then put -2 in. It's kind of an order of operations issue. Okay, so just looking at the order that we'd have to do this. The order of operations says first, number 1, we'd have to go and find out what f of -2 is. Get that done first. By the way, the answer for that, okay, when you do go and find out what f of -2 is, putting it into the original function, it ends up being -50. That's it, like just -50, right? It's like a math 11 thing. We're done. That is the y value for that x value. Now, step 2 says, hey, now that you've got that stuff, yeah, it's pretty boring. It's just a constant, -50. Okay, now do 2 derivatives. Of that -50. Well, geez, after the first derivative, the answer is 0. And after the second derivative, the answer is still 0. It's never going to change. So my answer to this question is, yep, pretty boring. You just asked me to do a derivative of a constant. Well, actually, 2 derivatives of a constant. So that is just not the way that Leibniz writes down trying to find the second derivative evaluated at -2. Instead, he would do it the way we have in example 10. And that finishes up our first day of looking at some quick rules for finding derivatives.